The trapezoid rule and Simpson's rule are just two examples of a bigger family of formulas for approximating integrals. They're called the Newton Cotes formulas. If you do a Google search on Newton Cotes, you'll get lots of information. This is not in our textbook, and I'm not going to hold you to it, but still I think it's interesting to see these in a bigger picture. The trapezoid rule essentially uses two x values at a time to get two y values and approximate the function by a linear interpolation in between. Okay. Simpson's rule uses three x values at a time, equally spaced, to get three y values and then interpolate between them using, or approximate between them using a parabola. Okay. And then in each case you find the area underneath that approximating function. So that would be the 2-point rule, this would be the 3-point rule. There's a 4-point rule that uses 4 equally spaced x values to calculate 4 y values and then approximate with a cubic function in between and then find the area underneath the cubic function. Okay. So in this case you could just use any n. In Simpson's rule you had to use an even number of subdivisions. In the 4-point rule, since you're taking these things 3 at a time, 3 intervals at a time, you actually have to have the number of intervals, n has to be divisible by 3, and so on. And there's one of these formulas for any number of points. I'm curious, just because the example that we did for Simpson's rule and the trapezoid rule, I used n equals 6. I looked up what's called the 7-point rule. The 7-point rule is going to use 7 equally spaced x values and approximate by a 6th degree polynomial. Okay, and what it said was that when you got these 1, 2, 3, 4, 5, 6, 7, you got 1, 2, 3, 4, 5, 6, 7, and you've got this approximating 6th degree polynomial. The area is approximately, the area under the 6th degree polynomial, which is an approximation of the area under the function, is given by, where do I have those numbers? It's 1 over 140 times delta x times 41 times f of a, so that's the a, then there's x1, x2, x3, x4, x5, and x6, which is b here. Let's just call it x6 because there might be more that goes on after that. So 41 times the first one, plus 216 times the second one, plus 27 times the third one, times f of x3, plus, where am I? 272 times the fourth one, and then 27 times the next one. I didn't take enough points here. 1, 2, 3, 4, 5, 6, 7. I do. How come I'm coming up? We got 41, 216, 27, 272, 27. Actually, because I can't count, that's why x1, this is an x2, this is an x3, this is f of x4, and then plus 216 times f of x5 plus 41 times f of x6. Okay, and then if you had another interval, you would do the same coefficients again. Notice that the 41 that's used for the f of x6 on this would also be a 41 that's used over there, but when you combine them together, that would turn into an 82. So using this to approximate the integral from 0 to 2, no, 0 to pi of sine x dx with n equal to 6, it looks like, well, 1 over 40. Why is this not writing here? 1 over 40, 140, times pi over 6 times 41 sine of 0 plus 216 sine of pi over 6 plus 27 sine of pi over 3 plus 272 sine of pi over 2 plus 27 sine of 2 pi over 3 plus 216 sine of 5 pi over 6 plus sine 41, sorry, times the sine of pi. This to me is just crazy. It's like I'm going to take 6 function values and I'm essentially taking a weighted average. I'm adding these things all up, but I'm multiplying them by different things and then dividing by something in the end here. Multiplying by a little width and essentially getting the area. Why is it that this y value is worth 216 when this one's only worth 27? Well, it just happens to be how it comes out when you find that approximating polynomial and then integrate that polynomial. Anyway, when you do that, type that all into your calculator, you get 2.000178114. So pretty dang accurate there, because we know the answer is supposed to be 2. Your calculator is actually doing something similar to this. When you use the numerical approximation button on your calculator, it's not exactly this, but it's related in that it's taking certain points in your interval, evaluating the function, multiplying them by certain coefficients, and then dividing by something out in front. Exactly which one it's doing, I was at a talk one time and I heard about it, and it's really a different way of generating these numbers, but it's very similar in that it weights some of the y values more strongly than others. Anyway, that's the Newton Cotes formulas just for your edification. Again, this is not something I'm going to test you on.